Hi everyone, I'm Tianle from Peking University, and I will join Princeton soon as a PhD student. So today I'd like to talk about something on the optimization of deep learning. And this talk is based on the joint work with my fantastic collaborators listed below. So here is the outline of today's talk, and I will introduce a recently developed technique for understanding the optimization of deep learning. And then I will show how to use this technique to give convergence guarantee for a problem that is harder than classic supervised learning. And in the end, I will show how these insights from the theory may inspire us to develop new algorithms. All of today's contents are very simple and only involve some basic calculus plus some mathematical intuitions. So I hope all of you can enjoy this talk. Yeah. Okay, let's get started. First, I noticed that our audiences are coming from very diverse background. So maybe let me give a very brief introduction about the learning problem that I will talk about today. So we will basically focus on the supervised learning in this talk, which includes classification and regression tasks, where we are given some samples xi and their corresponding labels yi. Our model can be represented as fwx, where w is the parameter of the classifier and x is the input. We have a loss function L of f and y, and the object under the principle of empirical risk minimization is the sum of L of fw, xi, and y. And the most popular method, which also achieved a huge success recently, is deep learning to solve this problem, where the model here in deep learning we use is over-parameterized deep neural networks, and I will explain what is over-parameterized later. So the optimization in deep learning is basically working on training neural networks with object in this page. I mean the ERM object. Okay. So from a theoretical perspective, the optimization of deep neural network is extremely hard to analyze, since this is a highly non-convex problem and our knowledge to deal with this kind of problem is very limited. We only have can deal with like convex optimization problems. So, and it is even more challenging to get a global convergence result, which means to show that the object will converge to a global minima instead of a local minima. In contrast, in practice, deep neural network can be trained to perform very well, even by very simple algorithm like gradient descent. I think all of you may have learned this algorithm in some like optimization, the basic optimization course. Okay. And even more, over-parameterized networks can be trained to fit random labels, which means the success of the optimization seems not to rely on the benign structure of the data. So in summary, in practice, the networks just can be trained very well, and the optimization seems to have no problem. Okay, so because of this stark contrast, it becomes a key problem of the whole deep learning to understand the optimization of deep learning, especially in theory. And so recently there is one attempt on attacking this problem that provides some insights. The basic idea is of this attempt is to exploit the over-parameterization in deep learning, which means the number of parameters is much more larger than the number of data. And note that this is very different from the traditional machine learning, where the models usually have the number of parameters much smaller than the number of data. Just for example, linear regression or some other method. Yeah. So how can over-parameterization help? Intuitively, more parameters can bring more capacity of the model, so the large model can fit the data much easier. And there is a series to support this from the approximation theory point of view, that over-parameterized networks can be used to approximate any function with some regularities, like continuous or something. Yeah, and the empirical study also found that the over-parameterized network can be trained to fit nonsense data, such as data with random labels, as I have mentioned. And this is very famous figures in the deep learning community that shows the training with shuffled random labels or shuffled pixels or some nonsense data can be converged to like near zero loss. Okay. So to summarize, the insights from the over-parameterization can be listed as below. First, over-parameterization brings some capacity, and so small change to the parameter W may be suffice to change the model a lot that may be able to fit the data just intuitively. And as a consequence, we may only consider the optimization problem in a small neighbor of the initial parameter W0. So these are the insights from the over-parameterization. And inspired by these insights, there is a bunch of work studying the convergence of over-parameterized neural networks under gradient descent algorithm, like Jacob et al., Du et al., Andrew et al., and Zhou et al. Okay, so the key ideas of this work are that over-parameterized networks are approximately linear with respect to the parameter in a neighbor of the initialization. We will show this later. And secondly, there is just a global optima inside that neighbor. So to be concrete, more formally, we can write down the idea using simple Taylor expansion of the function of neural networks at the initialization point. Again, as the FWX denotes the network with parameter W and input X, we assume the output of F is a scalar. In fact, we only focus on the scalar output in today's talk. So this can essentially be viewed as a linear model where the linear parameter is W minus W0 after the expansion listed below. Like the FWX can be approximated by FW0 the X plus W minus W0 times the gradient of W, the gradient of F at W0. So we can notice this is just a linear model with respect to the whose parameter is the W minus W0. This is with respect to W. So we are now ready to state the pipeline of the proving the global convergence of gradient descent to optimize over-parameterized neural networks. First, over-parameterized neural networks are approximately linear with respect to the parameter in the neighbor of the initialization. So gradient descent is applied within a not so non-convex regime. By not so non-convex, I mean that in this regime, the problem can be approximated by the linear. The function can be approximated by the linear, linear model. So gradient descent in this regime can have very good convergence guarantee. And so gradient descent can be approximately find the optima within this regime. And secondly, there is just a global optima inside this neighborhood since the over-prioritization brings a lot of power of expressivity, and so the optima in this region can the optima reached by gradient descent in this regime is approximately a global optima. Having developed some theory on this optimization, the optimization of deep learning, we are now to ask what can we do next. In this talk, I will talk about 2 points of view that we have taken. Firstly, we are thinking about choose global convergence for a harder problem. Recall that in the last slide, I show how the pipeline to prove the global convergence of the supervised learning, and I will show some how to use this technique to tackle some harder optimization problem. And besides, we ask whether we can draw some insights from the theory and develop algorithms which with better convergence rate in the supervised learning setting. Okay, so let's move on to the first part. I will introduce a harder optimization problem which draws a lot of attention recently in the machine learning community. In this setting, we will consider optimization in face of adversary. The motivation example is is this picture, which says that machine learning models, especially deep learning models like deep neural networks, are found to be vulnerable to adversarial attacks. That is to say, a model can easily classify the picture of the school bus on the left side as a school bus. But if we add some small and imperceptible adversary noise to the picture and get the new picture on the right hand, the model will classify the new picture as a ostrich or 鸵鸟 in Chinese. Okay, so this is a very serious problem in machine learning, since that the adversary may use some small perturbation to influence the decision of machine learning models in real world, which is very, very dangerous for some application that may face safety issue like automatic driving or something. So formally, we define the adversarial attack as follows. First, we are given the model FWX with input data X. And an adversarial attack can be defined as AWX, which find an adversarial example within the BX, where BX is the allowed perturbation set, like usually used as L2 or L infinity ball centered at X, which can guarantee that the perturbation is very small, so that it can not be recognized by like human, or by human, but it can be can influence the decision of the machine learning models a lot. So a simple and intuitive method to obtain a robust model is adversarial training. The basic idea here is just optimize on adversarial examples AWXI instead of the original example XI. I would like to point out that this optimization problem is much harder than the classic supervised problem, since the adversary has great power. And we can look at the object, and the problem can be non-convex because the adversary can map the original points to some. This map can be non-convex or bring some non-convexity, non-smoothness. Yeah. And if the adversary can find the most adversarial example in the neighbor, I mean, like it can call some, it can do some maximization, optimization. And then this problem essentially become a min-max optimization, because you see here, if the A, which is the adversarial attack, can reach some maximum, so the whole problem becomes a min-max problem. And so it's nature that is much harder than the classic supervised learning optimization problem. So for this harder optimization problem, we prove that gradient descent on this problem can still optimize the object to global minima when the network is sufficiently over-parameterized. So the idea again is considering the neighbor of the initial parameter W0, but the main obstacles here is the problem cannot be approximated by linear regression as in the supervised learning case anymore. So, and the existence of the optima in the neighbor is not clean. So the previous pipeline cannot be directly applied to this scenario. We show that though the optimization can be potentially non-smooth and does not have the nice property as linear regression, we can still approximate the problem with a convex optimization problem. And use this approximation, we can prove that we can find an approximate optima in the neighborhood of the initialization points. And we then prove the existence of an approximate global minima by random feature techniques. Okay. In this way, we prove the convergence of the harder problem that, or adversarial training on over-parameterized neural networks. So we then move on to the part that focuses on what algorithmic insights can we gain from the theory. So firstly, let us see the typical convergence result in the previous work, just by following the pipeline I have mentioned. We only need to focus on the convergence rate in the theorem. I draw this from the Du et al. The is very seminal paper, Du et al. 2018. And it essentially gives a linear convergence guarantee for the gradient descent running on over-parameterized networks. So the convergence rate here can be seen as 1 minus epsilon lambda 0 divided by 2 and to the power of k. Yeah, it's a linear convergence guarantee. Okay, so one question that I asked myself is that can we design algorithms that is probably faster, like such as have a higher order convergence rate? So the insights from the theory to inspire us considering the faster algorithms are first the optimization of over-parameterized neural networks can be approximated by the neural tangent kernel regression problem. Here, neural tangent kernel, you can just ignore this term. It's just the linear expansion I have mentioned. Just recall the linear neural Taylor expansion. And so the optimization can be approximated by some linear problem. Just keep this in mind. And secondly, this approximate problem can be solved by explicit formula other than applying gradient descent. Linear regression can be solved by some like canonical equation or something. it can be solved explicitly. So why not just use the explicit formula? So this is my the insights I can draw from the theory. So let's briefly recall the numerical expansion, just to focus on the equation that Fwx can be expanded as like Fw0x and W minus W0 times the gradient. W minus W0 becomes the linear parameters, and it can be viewed as a linear problem. Using a similar but slightly different expansion, we expand the Fw at Wt instead of W0. We have this expansion, like Fwx can be approximated by Fwt's x plus W minus Wt times the gradient at Wt. Okay, so again, we can treat this as a linear problem with respect to W minus Wt. We want the new f here to directly solve the y. In other words, we want the Fwt plus 1 xi to approximate or to be equal to y. So let's directly solve the problem that the linear approximation equals to y, and we get the opposite rule, like Wt plus 1 can be Wt minus some, like the solution of the linear regression with where the linear parameters is W minus Wt. Here the Jt is the Jacobian matrix, which is the whose row is the who is composed by the gradient of like the gradient W gradient of W, or the gradient of f with respect to W in the equation, the expansion equation. And f and y here is are the vectorized version of all outputs and labels. So here we get the opposite rule from so that the approximation can directly solve the problem that in the next step the approximation is just equals to yi. So you use this explicit formula, we are able to prove that the algorithm we can get correct convergence guarantee compared to the linear in the former works. And we also get some bonus from this new algorithm. First, unlike the classic second-order method, which usually involves hashing-like matrix, that is offside number of parameters times the number of parameters. This updated rule only involves matrix Jt transpose times times Jt with size number of data times number of data. And this matrix can be much smaller than hashing in over-parameterized regime, since the number of data is much smaller than the number of parameters. And combining with the mini-batch scheme, which is very widely used in training neural networks, the size can be further decreased, since the size of the Jt transpose Jt here in the mini batch with mini batch scheme can be reduced to the batch size times batch size, and usually the batch size is something like 128, like it's very small. So so combining with the mini batch scheme, the size can be further decreased. So the overhead of this algorithm compared to SCD is very small. So we conduct the experiments using this algorithm on some scalar regression tasks. Here, I like to mention that we do scalar regression since we focus on the scalar output problem, and to do like multi-dimensional output problem, there is still some obstacles, and it's out of the scope of this talk. So we conduct the experiments using the algorithm on some scalar regression tasks, and the empirical results shows our algorithm can outperform other methods. Our algorithm is the red line in the figures. So you can find that it can boost the training very much. Yeah, so this algorithm is inspired the theory developed for optimization of over-parameterized neural networks, and we can have sound theoretical guarantee, and the empirical performance is also very at least shows some potential to develop like higher order methods for like second order methods for the deep learning optimization. Okay, so that's for today's talk, and thank you for your time, and welcome to see more information in my website, tianle.website. And if you have any question, please contact me at the email address below, and I will probably I will upload the today's slides to my website, and hope you can enjoy this. Okay, thank you.
Okay. Thank you, Tianle. So. Okay, so thanks for your talk, and we have three questions. First question is that will training with over parameter costs longer time or less time? I mean, whether it becomes easier or harder for us to train, and why?
That's an interesting question, and. Firstly, I think regarding the optimization of one epoch or parameterized model obviously cost more time. But as for the whole optimization process, I would like to point out that over-parameterization can make the optimization landscape better, so that we may not stuck at some bad minima, and there are some works support this point. And besides, I would like to point out that over-parameterization can also ensure that the model can fit the data perfectly, and especially in the large scale data set. If we don't use some over-parameterized net model, we may not able to fit the data. Yeah, I hope I answered the question.
Okay, thank you. And the next question is, how do we get the initial parameter W0?
Sorry, I missed this point, and the initial weights are usually randomly drawn from some distribution like Gaussian, and in our theorem we assume the initial weights are drawn from the Gaussian with some scale. Yeah.
Okay. The third question. What's the proportion of parameters and data that can result in a linear approximation during optimization?
Firstly, I think the linear approximation always hold, but there truly exists some requirements for the number of parameters to ensure that under this setting we can find a global minima within a neighborhood of the initialization. So in our theorem, we require the weight to be like polynomial to the number of the data, where it's like usually be that n be the number of the data, then the weight should be like O n to the power 4, like this scale. And it's true that this scale is unrealistic, and in the practice, no one uses that wide networks. But I think that anyway, the theory can we can still draw some insights from the theory and over-parameterization serves as a beginning point to understand the optimization process. Okay, thank you.
Okay, and we have an extra question from your audience. Does mini batch also require small epochs? If so, will it truly reduce the time for convergence? There is no experiments to show this figure.
Yeah. That's an interesting question, and in fact, mini batch scheme is widely used in deep learning community, and also, firstly, we actually cannot. It's very hard to just use full batch because the number of data is quite large. And to answer your question, you say that mini batch scheme may make the training process be like slower or something. Then I would like to point out that if you don't use mini batch schemes, you may stuck at some local minima because or stuck at some settle point because the non-convexity of the problem. And if you use mini batch, you actually introduce some noise so that you can escape the settle point efficiently. And I think it's a little hard to compare these two scenario, and in the common setting, also in the practice of deep learning, we usually use the mini batch scheme. And
yeah. Okay. Thank you for answering, and we can end our talk now.
Okay, thank you very much.
Thank you, Tianle.